I would like to introduce Mr. Palmer. He is an engineering specializing in earthing, also known as grounding. Sorry. He has a expertise in all areas related to earthing, including design, audit, and test in sectors including power generation, delivery, heavy industry, mining, and rail. For over 15 years, Stephen has investigated and managed the risk associated with earthing, grounding, lighting production, and interference. As a leader of a team of 25 consultants and researchers, his experience extends well beyond the technical aspect of the field. Mr. Stephen has delivered formal earthing grounding training for more than a decade and has presented at numerous conferences, including NSW Government, ENA Engineers Australia, CIGRE, and IEEE. He has also been a consulting member of the committee responsible for the EZ0, AS3007, and AS2067. Mr. Stephen recently co-delivered a testing tutorial for IEEE Standard 81 and is a secretary of the CIGRE and CIRED Joint Working Group B3.35. Tasked to publish and substation earthing grounding design optimization, including the qualified risk. So this was a brief introduction of Mr. Stephen.
He is also the committee member of IEEE 80.
Okay, but it is not written here.
And CIGRE B3 has published a special publication on testing of earthing that was done under his leadership. So
great. Okay, thank you. Thank you, Mr. Niharaj. Thank you for writing. Now I will request to start the online presentation.
Stephen, please share your screen.
I have shared my screen.
Yeah, it's visible. You can change the screen as per your wish.
Okay, so you can see my introduction screen now.
he can.
We have one.
He can see your screen. You may start your presentation. Thank you.
Okay, so greetings from Australia. Thank you for the introduction. I am a specialist electrical engineer in power system earthing, and I am fortunate to serve on several IEEE, CIGRE, and CIRED groups that are dedicated to improving standards and guidelines around earthing system design and management, and specifically including testing. So I'm going to start today by recapping why we test and how we have traditionally tested. Then I'll present some newer, but still with 30 years of use, testing methods. And then lastly, some information on what standards and guidelines are heading towards. But first, let's recall that earth grids and earthing systems are critical assets and that they have three key purposes. They need to keep people safe, they need to protect equipment from damage, and they need to keep the electricity system operating correctly. Perhaps the most important purpose is to keep people safe by limiting step and touch voltages below safety limits, but all of those are important performance requirements of earthing or grounding systems. That's what earthing systems should do, but do they always work the way they should? Did they work properly in the first place when they were first designed and built, or have they changed since? We need to know if they are inadequate so we can make them safe, including repair where that is appropriate. But how do we work out whether they're adequate? How do we actually measure or prove their performance? Well, high current faults and chart recorders is a way that it used to be done. Probably the most true measure of how it will perform in a real fault, but it's expensive, and is it actually safe? Not the safest test, I don't think, but would have been fun. This type of testing, earth resistance testing, has been relied upon for many decades, and it has its place. It can sometimes indicate condition. For example, a single electrode can be shown to be continuous. It can sometimes indicate performance. For example, where a prescribed electrode resistance is actually the output that you're after. For example, if it was a lightning design or a static ground and there was a nominated resistance was the required performance. There is wide held concern that this type of testing is often used and relied upon beyond its suitable uses and cases. There are limiting factors as to when this test will be helpful and when it will be substantially misleading. Here's some of the common problems explained. Even if this test is used to only provide a grid resistance, there are many complications with the test that can impact the validity of the results. For example, if the remote electrode is not far enough from the ground electrode being tested, which may need to be hundreds or even thousands of meters away, the actual grid resistance would not be at the midpoint, and it may not even be at what's called the MER compensation point of 62 degrees. Also, it's reliant on electrodes being similar in magnitude and similar in physical size, which is only true for smaller earthing systems and for the higher resistances. Depending on the size and proximity of other local earths or grounds, the measured resistance can be out by a significant margin in the case of other conductives being in the area. Let's talk about another traditional test. Perhaps the most common of the traditional tests is to do soil electrical resistivity testing. This is a very important test. It's even more important to do it with an understanding of what the test results are going to be used for, taking into account things other than just the electrical measurement, things like geology, geography, visual clues in the area as to what kind of stratification or what kind of conductive interferences could be there. All those things help you form the right electrical model for the soil. And that model or a set of models is essential for designing and sometimes for testing analysis. So that soil resistivity data is then used for modelling. It's essential for us to do modelling. And you can even model and try and estimate all of the step and touch voltages and transfer voltages. But is that modelling approach accurate? Is modelling actually able to prove safe? Some people certainly believe it is, and some countries rely extensively on soil resistivity testing, simple electrode resistance measurements, and computer modelling. But perhaps that's a little bit indirect, and there are now options for more direct measurement of the earthing system that can create more confidence around whether it's doing its job or not. And these methods now aren't high current and dangerous. They're actually safe, they're accessible, and they're affordable. So let's look at the categories of testing that the newer, in the last 20 or 30 years, tests tend to fall into. If we're trying to work out whether it's doing its job, we can think of assessing an earthing system in two categories of tests. One is condition testing, which is designed to quickly show if damage or deterioration or improper modification is present and that it now requires some kind of corrective action. Performance testing accurately and efficiently identifies actual electrical performance, but we'll talk a bit more about that later. Let's dig into condition testing first. In IEEE Guide 81, it's referred to as integrity testing. In some parts of the world, it would be called continuity testing. But the idea is to demonstrate, to validate by measurement that everything that should be bonded together is appropriately bonded together, and that everything that should not be bonded is appropriately separated. You want to be able to achieve that quickly, efficiently, and with accuracy. Continuity or integrity testing is a powerful form of condition testing. It can identify not just broken or stolen connections or conductors, but it can even identify loose or deteriorated ones if the right equipment and the right approach is taken. Continuity testing can be carried out at every part of the substation and to every item in the station. This provides much greater accuracy than sample testing of specific points or a specific range of items only. It's testing every single thing. If the test instrument has good safety and noise immunity qualities, testing can be carried out in any station without de-energization or any disconnection. In fact, we tend to see around the world that earthing specialists are saying any type of disconnection is more dangerous than the benefit you get from measuring with that disconnection. So all of your testing methods should be aimed at being able to effectively measure with everything intact, in place, and not disconnected. So let's have a look at at an example of the continuity testing process. We establish a reference, we walk around with a probe and a meter, and we measure everything in the yard, trying to build an electrical picture to try and see even small changes in milliohms can indicate there's a problem. Here's a highly sped up video of a continuity test underway. This is 10 minutes to test this yard, and it's not just testing every structure or every item, but it's taking multiple measurements to every one, so that even where there are multiple risers on, say, the transformer in the middle, you can check every one of those connections. Of course, many stations are much larger, but the speed allows even the largest site to be tested very thoroughly in a short period of time. The blue lines are actual track traces of staff who have been doing continuity tests throughout those 2 yards. And you can see that even a very large station is less than a day. They're all hours, not multiple days. Let's move on to performance testing. The most powerful form of performance testing is earthing system current injection testing. In current injection testing, a small test current is circulated around a test circuit. The test circuit can be an overland lead passing current to simulate a fault, or the test circuit can actually include the injection of current over a power line or a cable. Being small, this current can be allowed to flow for hours while measurements are being taken. To allow it to be measured, even in a live station with a lot of electrical noise, the current is injected at a chosen frequency away from the power system frequency and any other noise. Highly sensitive current and voltmeters are used, tuned to the injected frequency and with very high rejection of other noise, such as induction and standing voltages. These meters can then be used to measure actual touch and step voltages created by the simulated fault. This is a very direct measurement, needing scaling only for fault magnitude and perhaps a small frequency correction. Measurements can be dramatically more accurate than simple calculations and even more accurate than numerical modelling. This is principally because calculations can only be made of what's known about the real world, and usually to a limited extent. Testing, however, is current flowing in the real world, and all things, seen or unseen, as well. Known or unknown, all of those things affect the results in the same way they will during an actual fault. So the buried pipe, or the conductive fence, or the steel reinforcing inside the concrete footings, all of those things actually affect the performance during a test and during the real fault. And that's via conductive connections, but also inductive connections as well. So we've got a simulated fault passing current. Now measurements can be taken of transfer voltages. And we can do a voltage traverse by starting at the station and measuring the voltage at distances away. If you see in the bottom left there, a graph of the green line, the light green line at the top. As you move further away from the station, the voltage you're measuring is showing you an increase, which is the inverse of the EPR of the station. So we can use fall of potential tests to accurately determine the earth potential rise, even in an energized station. We can also measure transfer voltages, say to pipeline assets or telecommunication assets or anywhere else where we're trying to prove that our voltage rise has degraded, has lowered to an appropriate level by the time it gets to those assets. It's not necessary to measure the current splits or distributions, current distributions. It's not necessarily to do those to determine the EPR or to measure step and touch voltages, but it is if you want to determine the grid resistance or the other component impedances. So if you want to measure the current to determine those things, you've got to ask, where will I measure it? And do I need phase to measure it? Using, again, a frequency tunable meter, and now with a Rogowski coil, which is an air cored open-ended CT, which can be wrapped around conductive structures, the current through any of those conductive structures can be directly measured. This allows determination of coupling factors for lines and cables and input impedances for neutrals and any other conductive element. Even current flowing through fences and water pipes can be measured. When these currents are correctly summed, it can allow a very good estimate of the actual grid resistance and of the other component impedances. The results of performance testing can be very helpful in demonstrating safety and compliance, and they can help focus any remedial work where it is most needed. Of course, to be truly accurate, measurements must include magnitude and phase, and this is true for current in particular. If you look at the graph in the bottom right, the blue line at the bottom is a vector of the injected current for the fault, and the various colours climbing back up to the top left are current splits that have been measured, including their phase angle. The black vector is the residual current, which was passing into the soil through the grid. So how do we measure current splits with phase when we're up the top of a transmission line measuring a shield wire, or when we're in a cable pit on a screen, or when we're on a neutral? Measurement of phase wirelessly is made possible by using a GPS clock signature. So a very accurate clock, setting your source to a particular timing of the clock, and then measuring every other current and voltage compared to that, gives you wireless phase. If you lose the GPS clock, then you're relying on highly stable crystals or some kind of compensation for crystal drift to make sure that you retain good phase accuracy for some time, if, for example, you're in a cable basement or in a tunnel. So, modern, powerful, very illuminating techniques. You can learn a lot about how any earthing system is working by essentially simulating a fault and then conducting an investigation where you look into what are the voltages created, how is current passed, how is it conducted elsewhere. So these techniques are actually what's being spoken about now in emerging standards. So in IEEE 81, which was originally just on soil resistivity testing, but it's now on all kinds of grounding testing, there's changes in there that I expect will talk about proven methods, won't talk about instruments. There's a very important line to be drawn where we talk about methods, but we don't talk about any particular brands or styles. There will be more guidance than there's been before on integrity testing, and there's a lot more guidance on current injection testing and the measurement of current splits. IEEE 80 traditionally gave a lot of approximate guidance, and it's proven to be incredibly approximate in some cases. So measurement is turning into a very reliable way to tune your designs around what current distributions really will be. So expect in the next year or two a new edition of IEEE 81 with a lot of new guidance on effective, reliable emerging test methods. But there's another document coming out as well that you might want to have a look at too. I am the convener of the CIGRE working group B354, and as was mentioned in the introduction, we're focused on earthing testing methods, and we're charged to look at historic approaches, developments. I don't know if it's recent, if they've been used for 20 or 30 years, but the emerging best practice is what we're really looking for. And there's going to be recommendations about where things can be used and where it's not so appropriate to use them. Some of the key considerations are on the screen there. And these are topics that have been debated by members of our working group in our meetings now for several years. COVID was a bit of a disruptor to us as well. We didn't make the progress that we wanted to for various reasons, but we're now well underway and we expect to publish our technical brochure sometime before the end of next year. But there's some very important concepts there, all of which will be talked about in the technical brochure. The technical brochure we've decided also needs to recap some of the key physics that is required to analyse and to understand earthing properly. I've spent nearly 25 years now as an earthing person, and I've surprised myself that I'm not bored yet. But I have realised the most fascinating part about earthing or grounding is that it's what happens when the electricity escapes. It's when the electricity flows wherever it wants to. And it's the unknown certainty, it's the unknown paths that it will take that make it very interesting. The most helpful part is that the physics that drives the flow of current and that explains the amount you get and the voltages associated with the current flows, that physics is the same as every other part of electrical engineering. So a recap here of the physics and a bit of an explanation as to how it applies in that earthing space will be key parts of the technical brochure as well. And I think the technical brochure will highlight condition testing and performance testing as the two major categories, and a lot of different methods in each of those, not just the ones that are probably more mainstream that I've presented tonight, but some other approaches as well will be talked about to some degree. So if you have an interest in earthing testing, this is where I plug CIGRE. If you have an interest in earthing testing, if you've done some, if you've supervised it, if you have other people that do it, we'd really like you to go to earthingsurvey.com, complete the survey for us. The technical brochure will include a complete analysis of what we learned through that survey. We already have a lot of responders and we want more. It's not, we're not trying to get one or two from each country. We're trying to get as many as we possibly can, and we've got some pretty good smarts behind the survey to be able to sort, filter and conclude trends within countries, within regions and across the world. So the more we get filled in, the better, I think. That's Safe Earth. I've got to just put one slide up so you know who we are. And if you'd like to know any more about Safe Earth, just go to the website or send us an email. Thank you for your attention. Wish you all the very best for the rest of the conference. And if there's time, I'm happy to take any questions.
Mr. Palmer, we will be coming back to you again for the questions because we have a shortage